Hello viewers, thank you very much for watching GIFT TV. Today's video will be looking at when to use the appropriate correlation techniques. Specifically, we will be looking at correlation and scale of measurement. Let's get into it. A variety of statistical tests can be used to answer the question of whether two or more variables are associated or are independent. Which one to use depends heavily on the scale of measurement. Now the question is, what is correlation? Correlation is a statistical technique that can show whether and how strongly pairs of variables are related. So it can show whether the variables are strongly related, okay, or in terms of positive or negative, or if there is no correlation. So if you look at this chart, in the first quadrant, you see that we have strong positive correlation, that Y and X are strong and positively related. Then if you look at the second graph too, it's positive correlated but not strong, maybe moderate. Okay. And you come down here, you see that there's a negative correlation and here no correlation. All right. Now the question now is, what is scale or level of measurement? Okay, the concept of scale of measurement is the same as the level of measurement. Because the type of technique, the correlation technique that you want to use depends on the scale of measurement. Let's look at what scale of measurement or level of measurement is. Level of measurement or scale of measurement is a classification that describes the nature of information within the values assigned to variables. In research, there are 4 different scales of measurement. The first is nominal scale, ordinal scale, interval scales, and ratio scale. With respect to nominal, for which some characteristics is classified into exhaustive, mutually exclusive, but not ordered category. All right, so the category that you are using should be binary or categorical, but the level should be exhaustive in terms of mutually exclusive. If you take, for example, gender, okay, you have male and female. You take the education level, you have maybe no education, basic till you get to the university or tertiary education. It's supposed to be mutually exclusive. Okay, that's a definite category. Now, then we have ordinal. For ordinal, it takes into the characteristics that are classified into exhaustive, mutually exclusive, but ordered category. The difference between the nominal and the ordinal is that the category for ordinal is ordered, is rank, okay? But for nominal, it's not ordered, all right? So for a case of, let's say, socioeconomic status, okay, or social status is ordered, all right? So you have to take note of that. Or maybe if you are rating, all right, then you need to look at that as well. The next one is interval, for which some characteristics classified on a scale which permit it to be measured exactly. Okay, that is, for example, you have age, using established unit of measurement that can be added or subtracted in terms of the units as years. So if we talk about age, we can measure it in years. All right. Then we have the next level, that is a higher level, called the ratio scale. It has all the characteristics of the interval scale plus non-arbitrary 0 point. So that numbers on the scale may logically be compared as ratios. All right, let's take note of that. Let's look at some examples of the study variables and their level of measurement or scale of measurement. We have employment status, which is categorical, 3 levels. All right, so you see it's nominal. Gender is dichotomous. It has 2 levels. That is binary in nature, nominal. You have education level, you have 4 levels. We look at that, we have high school, associate, bachelor's, master's, and doctorate. It's ordinal, it's ordered, it's ranked. We have the residence, which is also binary or dichotomous. Okay, that's the dichotomy. So 2 levels, nominal, categorical, 5 levels for race, nominal. So if you look at it, we have several examples. You have institutional rank, institutional characteristics, they are all nominal. We have baby length, baby weight, they are in numbers, which falls under interval and ratio level. We have car price is also numbers, width of windshield wipers. They are also numbers, that is interval and ratio level. We have elevation, that is measured in meters in terms of the distance above the sea level. We have it also measured in meters, that is numbers, it falls under interval ratio level. We have air pressure, is also numbers, interval ratio level. We have socioeconomic status that have 3 levels ranked from low, medium, high. That is ordinary because it is ranked. We have income level, also ranked 3 levels, less than 50K, 50K to 100K, and over 100K. That is also mutually exclusive. It's ordinary. We have the satisfaction rating, that is 5 levels. It's also ranked extremely dislike, neutral, like, extremely like. It's also ordered. These are some of the examples of scale of measurement and study variables. All right, so now, when do we use either Pearson's or Spearman rank correlation techniques? The Pearson's correlation coefficient is typically used for jointly normally distributed data. For non-normally distributed continuous data, such as ordinal data or data with relevant outliers, a Spearman rank correlation can be used as a measure of monotonic association. Take note of that. Spearman correlation applies to ranks and so provides a measure of monotonic relationship between two continuous random variables. It is also useful with ordinal data. Take note of that, ordinal data, and it's robust to outliers, unlike the Pearson's correlation. Okay. So if the assumptions of the Pearson's are not met, it might be worth trying Spearman's rank. So for Pearson's correlation coefficient, is the most way of measuring a linear correlation among interval ratio variables. It is a number between -1 and 1 that measures the strength and direction of the relationship between two variables. That is, if the number is equal to -1, it means it has a perfect negative correlation. All right, so in terms of +1, it means that it has a perfect positive correlation. So if you look at this particular table, we have the various interpretation range, correlation type, then example. So let's look at that. We look at the first column, that is the Pearson correlation coefficient. We have between 0 and 1, we have 0, then we have between 0 and -1. Between 0 and 1 indicates positive correlation. Interpretation: when one variable changes, the other variables changes in the same direction. So if baby length is increasing, baby weight must also increase. It means they all move in the same direction. So the longer the baby, the heavier their weight. Whenever you have probably a Pearson correlation coefficient equals to 0, it means that there is no correlation. If there is no correlation, there is no relationship between the variables. Take, for example, car price and width of windshield wipers. It has no correlation. So the price of a car is not related to the width of its windshield wipers. The next is between 0 and -1 indicates negative correlation. So if you have a Pearson's correlation coefficient value of, let's say, -0.4, it indicates a negative correlation. So when one variable changes, the other variables also changes in opposite direction. Take, for example, elevation and air pressure. The higher the elevation, the lower the air pressure. Take note of that. When do we use contingency coefficient? The contingency coefficient is a coefficient of association that tells whether two variables or data set are independent or dependent of each other. So if the contingency coefficient value is near 0, you can conclude that your variables are independent of each other. Then there is no association between the variables. However, if the value is away from 0, close to 1, there is some relationship, okay, and can only take a positive value. Take note of that. Contingency coefficient value can never be negative. You can always take positive values. So the value of the coefficient lies between 0 and 1 and never attains 1. Okay, it's always asymptotic. It can never touch that one line. So when C equals 0, it indicates complete disassociation. And a value near 1 indicates a high degree of association. Contingency coefficient is particularly informative if you are working with a large sample and you don't need to find out if an association is complete or not, but you just want to know whether or not association exists. Then you can utilize contingency coefficient. Measure of association of dependent variables with independent variables in the study. So if you want to measure the association of the dependent variable with the independent variable when we are dealing with categorical variables, could be nominal, could be even ordinal, we can still use the contingency. But the appropriate for contingency is that whenever you are trying to measure association between categorical variable for dependent and independent variable, then first you need to try the contingency coefficient. Very important. Other alternative measures of association include the phi coefficient, which has the same weak point as the contingency coefficient, never reaches 1. And Cramer's V as well is also another form of association measure when we are dealing with categorical variables. Cramer's V is often preferred because with perfect association, it becomes exactly 1, no matter how large the table is. So sometimes it's preferred to that of the contingency coefficient and the phi as well. But when do we use phi coefficient? In statistics, the phi coefficient is a measure of association for 2 binary or dichotomous variables. So if you're dealing with categorical variables in terms of just two, that's binary or dichotomous variable, then you have to look at the phi coefficient. The phi coefficient is a measure of the degree of association between 2 binary variables. It takes on values between -1 and 1, where -1 indicates a perfectly negative relationship between the 2 variables, 0 indicates no association between the 2 variables, and 1 indicates a perfectly positive relationship between the 2 variables. The interpretation of the phi coefficient is similar to the Pearson's correlation coefficient. So the same interpretation for Pearson's applies to the phi. Measure of association among dichotomous independent variables, you have to use phi. If you look at the case, we have institutional characteristics, which has 2 categories. It's binary, it's dichotomous. And institutional rank 2 as well is also binary. Residence was whether, it's also binary. Gender was binary. So once you are looking at association tests among binary or dichotomous variables, it's a good idea to use phi coefficient. When do we use Cramer's V? Cramer's V is a measure of the relative strength of an association between 2 variables and ranges from 0 to 1, with 1 indicating perfect association. A Cramer's V of 0 indicates no association between the variables. Cramer's V of 1 indicates a very strong association between the variables. In practice, a Cramer's V of 0.1 is a good minimum threshold for suggesting there is a substantive relationship between 2 variables. Measure of Cramer's V. Measure of association among categorical independent variables with different number of levels. So if you are looking at a case where you are studying variables at different levels, we have binaries, we have 3 levels, 4 levels, 5 levels, and you want to measure the association, it's a good idea to use Cramer's V. That is why I stated earlier that it is preferred, the most preferred as compared to that of the phi and the contingency coefficient. Because this one covers all levels. So if you look at this case, we have 2 level gender, we have education level 4, we have 8, we have 3, that's financial aid, 3 levels. You have residence, 2 levels. Ethnicity, 5 levels. Institutional category, 2 levels. Institutional rank, 2 levels. So you see that in this particular case, we have different categorical variables that we are including in the study. Therefore, it's a good idea for us to increment V to minimize the margin of error. When do we use Kruskal gamma or UQ? Gamma can be calculated for ordinal or ordered variables that are continual variables like height or weight, or discrete variables like hot, hotter, and hottest. They are ranked. While there are other coefficients that can calculate relationship for these types of variables like Somers D or Kendall-Tar, Guzman's and Kruskal's gamma is generally preferred for when you have many tied ranks. It is also particularly useful when your data has outliers, as they don't affect the results much. For some field of study, it may be the preferred method for all ordinal data arranged in a bivariate table. If you have 2 dichotomous variables, for example, responses that are yes or no, use Q instead. Okay, so if in your data set you have 2 dichotomous variables, that are added to ordered variables, instead for you to use the Kruskal gamma, it's a good idea to use the UQ. All right, even though UQ is for ordered, but it's also helped to minimize error whenever you are dealing with ordered variables. That also takes into account some element of binary variable as well. But if you use Kruskal gamma, in such instances, you may get the estimate wrong. So try to know the difference. If you look at the table here, we have the Guzman-Kruskal gamma test. All right. So you see that we have education level, we have the socioeconomic status, you have income level, you have satisfaction rating. They are all ordered. So in this case, it's a good idea to stick to the Guzman-Kruskal gamma. However, if let's say we have gender, okay, we have gender here, and the rest are ordered, it's a good idea to use the U-skill. So U-skill is a good technique to use to measure correlation whenever you have a mixed data for ordered and binary variables. Thank you very much for subscribing to GIBS TV, and I see you in the next video.